plays a leading role in the UK's advanced electronics industry, and we work closely with the governing bodies, societies and academic institutions and industry to ensure that we're kept up to date with the latest developments and innovations. And this society, our objectives is to provide regional seminars, workshops and international conferences and exhibitions. And as we move towards more less socially distancing opportunities, we can start then getting our events back to the original format that we intend, which is a face-to-face event. But as we recognise going forward, there's probably an opportunity to hold more of these online events as well. So as these times are changing, it then leads us into power electronics and machines and drives technology, which is also changing. And this is a great time for people to get engaged with this technology. There's a lot of opportunities for growth and exploitation coming forward. And the range of speakers that we have going forward is going to give us a range of information from the DER challenge itself, which is part of the UKRI governing bodies, all the way down through industry and the RTOs to academia. So we hope this is a great event for you. And yeah, please feel free to feedback any recommendations or comments after the event on this. And IMAPS UK is your local chapter, so any recommendations on topics or anything like that, please send them on to us, and we aim to deliver this continually to help develop the power electronics, machines and drives community in the UK and globally. So the benefits for members, you can get access to the IMAP source, which is a research portal, which is mainly housed by the US chapter. And there's very competitive rates in terms of membership fees. And for students, it's free. So please sign up and start learning and networking and sourcing these great opportunities going forward. The future events programs that IMAPS UK has put together. So there's another online tutorial in a couple of weeks on new product introduction by Alan Proudfoot. And if anyone has any opportunities that they want to share for the community in terms of tutorials in this area, then please feel free to get in touch with the Secretariat with your ideas, and we can get you online as well to share your knowledge. Our inaugural event, Microtech, obviously was postponed in March, so we've moved it to September, and recent decision has been to make that an online event. We don't feel it's going to be easy to get a face-to-face event for that, so watch out for more information being communicated to the members on that. The actual date is still to be confirmed, so we are planning the last 2 weeks of September to run that event. And then in November, we've got a sensors packaging event, which is focusing on obviously how to package sensors, and that is another interesting area, particularly with IoT devices becoming more and more critical for big data acquisition in I40. So just to get onto the agenda, we've got a full day with sessions with breaks in between, and in those breaks, as Bob was saying, there's a short survey that we put together for each session. If you could spend at least a maximum minute on those couple of questions, it just gives us a bit more information on what the wider audience is feeling in these areas for development, and I'll talk more about those as we go through the day. And just for the speakers, as it's going to be critical to keep on time. So without too much further ado, I'll get on to the speakers. But just to give the speakers a warning of what to expect as a 5-minute warning, this is what sound you will hear. So yes, if the speakers could then start wrapping up when they hear that noise with about 5 minutes to go, that should hopefully give us some time for some questions at the end of each presentation. Please submit your questions to the question section for each speaker. If we do have time at the end of each presentation, we will be able to answer those. If not, we'll hopefully be able to address those in the break. So at that point, I'd like to now introduce our first speaker. So we have Martin Cherrington from DER. So Martin Cherrington is the lead innovation for the Driving the Electric Revolution Challenge, which is part of the Industrial Strategy Challenge Fund, and they're developing the UK supply chain for power electronics, machines and drives. So over to you, Martin, and hope everyone has a really good event. Thank you.
Almost forgot to unmute myself there. Good morning, everybody, and thanks for the introduction, Liam. I shall certainly attempt to beat the bell. So I guess I've got the fortunate job of being first in the day, so I get to do the scene setting for you all. So I'm going to talk to you today about driving the electric revolution and about what we're doing in terms of building the supply chains for power electronics, machines and drives. So I'm going to give you a bit of an overview of what we do with the challenge. Then we're going to look at a fairly brief run through some of the key thermal challenges faced around power electronics, and then really move on to the opportunities that exist for you guys as to how you can actually look at hopefully industrializing your new novel solutions and getting them into product, and then we'll do a bit of a short wrap up following that. So moving on to the challenge overview. So driving the electric revolution is part of the Industrial Strategy Challenge Fund. So the modern industrial strategy was launched back in 2017, and there were four grand challenges that emerged at the forefront of the strategy. So these were aging society, AI and data economy, future mobility, and clean growth. And the Industrial Strategy Challenge Fund was then born with a view of how can the UK increase its GDP spend to 2.4% for research and development activity from what was then 1.7%. I certainly won't mention anything about the current economic climate and the effect of GDP. But to date, almost £3 billion has been committed by the government across 21 challenge-led or challenge-themed programs, of which Driving the Electric Revolution is part of the third wave of this. And Driving the Electric Revolution falls officially into future of mobility, as an awful lot of the activity that we do focuses around a lot of transport-related themes. However, we also really see ourselves as probably even more importantly falling into the clean growth. So we are essentially enabling decarbonisation and allowing or helping us as a society to eventually become more and more, I guess, eco-friendly, for want of a better way of putting it. But where do we actually sit? So trying to put DER into a bit of sort of broader context. So the industrial strategy is being delivered by UK Research and Innovation. UK Research and Innovation was formed a few years ago, and essentially brought together these 9 existing research councils, including Innovate UK and EPSRC, and DER. Driving the Electric Revolution is being delivered by Innovate UK and EPSRC, and UK Research and Innovation reports directly back and is sponsored by the Department for Business, Energy and Industrial Strategy, and that's our main link back into UK government. So why is there such a focus on power electronics, machines and drives? I'm sure I don't need to tell any of you. I've probably already said it already, but electrification is indeed happening apace, and you know, I've mentioned the whole fact that we sort of see ourselves as fitting into this sort of green clean growth area, but really current government legislation from things like net zero by I think we're up to about or forward to about 2040 by now. I think there's eliminating diesel from rail rolling stock, trying to eliminate diesel from automotive, and these target dates are ever being brought forward, and all of these sectors represented by these images are all electrifying. So whether that's from automotive, whether that's the energy sector, and that's both from energy generation, so things like offshore winds, to looking at photovoltaics, for instance, for the more renewable energy side, to energy distribution. So actually looking at improving grid efficiencies, to looking at charging infrastructure and creating rapid chargers. There's off-highway vehicles. So that is both construction and agriculture. There's also industrial drives and robotics on the right, a huge sector for the UK. A huge amount goes on. Moving into the bottom right, we have the marine sector. In the middle bottom, we have rail, and that's both rail rolling stock is increasingly being electrified, and we need to also focus on the infrastructure. And certainly Network Rail have got a huge job on their hands trying to electrify the rail network, as I think at the moment it's only just about 50% of the rail network in the UK that's actually currently electrified. And last but by no means least, the aerospace sector. There's a huge amount going on in the aerospace sector, both from the sort of the more electric aircraft type principle of essentially creating sort of a more hybrid type approach, to fully electric propelled or electric propulsion planes. So what is Driving the Electric Revolution all about? Well, we are an £80 million industrial strategy fund Wave 3 challenge. We started around about August last year, and our primary focus is on supply chain development for power electronics, machines and drives. And I'm sure a number of you have probably already heard, but we have this mission statement that Driving the Electric Revolution will be the catalyst to growing £5 billion more power electronics, machines and drives products in the UK by 2025, and doing that across across any sector that is electrifying, to invest and collaborate with academia to ultimately establish these supply chains. And what are we all about? So I've already said we are focused on all sectors. That's any sector that is electrifying. We want to work with you. We cover the whole value chain, the whole PEMD supply chain, and that's the entire life cycle, all the way through from raw materials through to manufacturing integration, and then all the way off the other end to materials recovery, recycling and reuse. As I've said, we are all about developing UK supply chain and manufacturing capability. That is both in terms of meeting demand for UK markets, making sure we can meet our own domestic supply, but also that we have a surplus that we can actually look to grow our export market. And ultimately, we want to be able to help our SME community grow. Obviously, to do this, we do need world-leading facilities to help businesses develop this capability, to ensure that we do stay globally competitive. And we need we need to look at this prototyping and scale up capability. So we've already funded 14 projects, investing about 7 million, which I'll mention a little bit more on later, specifically focused on the component supply chain. But we also announced, I believe in March, a £30 million investment in the John Next Revolution Industrialisation centres that hopefully you've all heard of. And again, I will mention a little bit later on. But they are very much there for industry to use. And again, I will mention the elephant in the corner of the room there, skills. Skills, particularly in terms of electronics engineering, is a really big challenge. And we do have a certain amount of our £80 million budget to spend on doing something in skills. But all I'll say on that at the moment is watch this space. So moving on to the thermal challenges. So thermal challenges of power electronics. So if we look at it from a very high level at the moment, so essentially solving challenges requires collaboration, and it really requires the sum of all parts. So that's, whether you are working in devices, whether you're working in housing, whether you're looking at the component side of things, whether you're looking at the application, the design side, the integration, and the manufacturing. Ultimately, you all need to work together, and that's where hopefully DER as a challenge can help you form those collaborations, and ultimately the result of that will be creating these UK supply chains and hopefully having product that's actually made in the UK. But why is thermal or why is thermal management so important? Well, again, I'm sure I'm speaking to the people that know far more on this than me, but ultimately the real killer for power electronics device reliability and lifetime is ultimately temperature cycling, and it's a critical factor for reliability and performance. And there's lots of interesting new devices coming forwards, certainly in the compound semiconductor wide bandgap area, including silicon carbide and gallium nitride, that provide a potential solution to this. Indeed, I think you're going to hear more from Mark Johnson on the wide bandgap challenges later on this morning. But whereas silicon carbide might be able to, in theory, operate up to around about 500 degrees, the actual packaging materials can't quite cope with that at the moment. And as this drive for efficiency increases, and really that's because the continued drive to increase power density brings on a further need to reduce these losses and improve the efficiency in the systems. And to do that, these systems are getting hotter and hotter, and we need to address these. And there's a lot. There's a lot of interesting work going on around thermal interface materials at the moment. In electronics packaging, looking at things like ceramics, metals, plastics, composites, and they've all got interesting issues around using so many dissimilar materials. Creates all sorts of issues around the coefficient of thermal expansion. And the interesting thing is that all these problems are ultimately sector agnostic. The challenges themselves are fairly common, and actually that does open the door for people working in different sectors to actually work together as a group to try and solve these issues. And whilst the challenges themselves may well be fairly similar, the solutions aren't necessarily always the same. But ultimately, if you can come up with a good thermal system, this will ultimately lead to you be able to realize higher power densities, smaller packaging size, and ultimately increase your device efficiencies. So really the big issues in power electronics, I guess this is more I guess this first one's really sort of almost the water pressure analogy, but as you increase power density, the challenge to actually remove the heat becomes harder and harder. So you need a greater temperature gradient, or some sort of new method to use it to actually get rid of sort of the water pressure in a pipe almost. And as this heat flux increases, designers need to continue to push for smaller and lighter solutions. Heat dissipation is absolutely critical to get the heat out of these systems. In particular, with the projected uptake of wide band gap power devices, it is increasing as more and more of the big manufacturers realize the potential efficiency improvements that these devices can do. Certainly, if you look at automotive and off-highway, certainly there's a real interest at the moment in silicon carbide devices, certainly in terms of looking at converters and traction inverters, and ultimately improving the efficiency in those systems. Well, it certainly leads to in real terms, significant increases in vehicle range by reducing those losses within the semiconductors. And certainly, if you look at things like the energy and the rail sectors, and you look at the effect that the increased uptake in solid state energy conversion is having, so moving away from transformers to do your power conversion, and looking at using power electronics instead, the increases in grid efficiencies there through minimizing the losses has been great. And certainly if you look at some of the examples in Japan, where they've managed to using wide bandgap technology, they've managed to improve their power conversion efficiency and reduce the loss in the grid, that they've actually been able to offset the need to actually install new power stations. And you also look at the national grid, not national grid, even so network rail are doing more and more at the moment in some of their latest electrification work of actually doing more and more, looking at more and more solid state power electronic solutions to power conversion. But ultimately, our challenge, the Driving Electric Revolution challenge, is very much focused on this sovereign supply chain, looking at catalyzing this clean technological innovation without using too much of the buzzword bingo. And ultimately, thermal design is absolutely critical to our success, and this is where hopefully many of you here today can actually help us in this fact. But it's all very well having the answers to the question, if you like, having the solutions to the challenges, but the real challenge lies in this industrialization. So we need to be able to take these new ideas, and we need to be able to actually scale them up. So whatever the new packaging solution is, whatever the new interconnect technology is, whatever the new thermal interface material you've come up with, we need to be able to actually scale them up to be able to meet the demand, and we need to make sure that the supply chain can cope both upstream and downstream. So we need those supply chains to be innovative and robust, and ultimately, to do that, we need to ensure that there's significant collaboration with the ultimately with your end customer. So moving on to the opportunities side. So we are the Driving Electric Revolution team are very much backing collaborative UK supply chains and manufacturing. Although our focus here is very much it's not about the what you make, but the how you make it. So what have we done to date? So I mentioned a few slides back that when DER launched as a challenge, we launched a competition around accelerating the component supply chain, and we have invested just under £7 million in 14 projects, engaging around 38 organisations. And a number of these projects are specifically looking at addressing thermal challenges. And whilst I can't go into too much detail for obvious reasons, there's three quite interesting examples here. One of which is a project actually looking at interesting die attach processes in motor controllers. To try and increase the cooling rates. Another is looking at some interesting condition monitoring of IGBTs, and ultimately this really is about being able to see what's actually going on inside the device, and actually being able to take that information about what's going on. And allowing future designs to be improved upon. And another one, thinking of more passive components, is actually looking at film capacitors and actually trying to improve their temperature operating range, looking at the metallized dielectric. So the other thing I mentioned is we have industrialisation centres. So we've put 30 million into this. Their main objectives to run through this apace. So really investment and growth. They want to encourage reshoring, and they want to work with the business community to help them grow and develop, and ultimately encourage export. They want to encourage industrial engagement. They want to work with the community to understand where the gaps in the supply chain are and make sure that they have the capability available to help industry solve those gaps and fill those gaps. And then there's the skills development piece, which again I'll leave there at the moment. But ultimately they're looking at essentially trying to leverage capability that currently exists within industry, academia, and the RTO network for the benefit of everyone. And you can think of these centres essentially as almost a bit of a hub, so sort of this sort of value chain model. So industries continually feeding in what it needs, and in return they're getting this additional support. And also the centres provide a direct link back to government and back to the DER team at UKRI, but also into the devolved administrations. So again, if you haven't currently engaged with the industrialisation centres, I'd strongly advise you to take that opportunity. In terms of future opportunities that exist, so we are about to launch another funding competition around accelerating the PEMD supply chain. So these, we have up to £5 million available in the pot to fund 3 to 9 month collaborative research and development projects between 100,000 and 500,000 in total costs. And these are focused on development of supply chains and capability, with a focus on this sort of industrialisation. So again, it's thinking more of process development and supply chain development, rather than pure technology development. It's about taking your concepts and industrialising them. By the autumn, we hope that our centres will be fully operational. So again, please do make contact and keep an eye out next year. We will have future there will be a future funding competition appearing for longer collaborative R&D projects. just 4 current themes of interest that may or may not be related to the upcoming funding competition. But we have four themes around which I think will be of interest in terms of industrialisation of materials and packaging processes. So there's process development, so it could be scaling up of these processes, increasing automation of these processes from a design for manufacture point. It could be about integrating your new material into the project, or it could be about ensuring that you can actually meet the potential demand. From a virtual process development side, you could have created a pilot process at the moment, and you want to ultimately scale it up and use modelling and simulation to do that. From a testing and validation side, you could well need to look at scaling up or potentially automating a new testing and validation process from a QA/QC process, ultimately improving the quality of your product. And then there's the circular economy side of it. So just to summarise and bring this to a close, then. Before I get cut off in time.
Martin, yes.
Yeah, no problem. So ultimately, thermal management is critical to realise efficient electrification, and integration of new materials and packaging solutions into products, both new and old, and the industrialisation of it we recognise as a huge challenge. But we hope that Driving the Next Revolution is there to actually help industry do that, help you build the supply chains needed to ensure that we have this sovereign capability. We can make things in the UK, and to help us meet some of these environmental policy targets. And ultimately, we can help in a few ways, either by doing that coordination work, facilitating those new connections for you, providing you with the funding opportunity and the opportunities to actually do these projects and actually realise this industrialisation, and also provide access for you to resource and capability through our industrialisation centres. But ultimately, it's in terms of Driving the Next Revolution, it's not about what you make, but how you make it. So with that, thank you very much.
Thanks very much, Martin. That's a great overview of the DER call, and we're hoping that this funding will accelerate the growth. There is one quick question, but maybe we can address that in the break for yourself, Martin, to look at that one. So thanks very much. So next on the agenda, we have Steve Riches from TribusD, who is going to talk about how high temperature materials and processes can be applied to electronics packaging. So Steve Riches is obviously it's Secretariat for IMAPS as well, and he's obviously got TribusD as a company. It's previously worked extensively in the microelectronics industry and predominantly GE Aviation, where I met Steve a number of years ago. So Steve, over to you.
Thank you, Liam. Good morning, everyone. I hope you can all see my screen okay. Today, I want to talk about some of the experiences we've had on sort of developing high temperature materials and processes for, in particular, aerospace type applications, and see how it can be applied to power electronics packaging. I think what we'll see is there will be a number of pointers which will be covered later in the day through more specific presentations. So it could well act as a sort of like a packaging introduction, and then more details on some of the things which have been developed will become clear through the day. Right, okay. Sorry, there's just a bit of a lag in the movement of the slides through. So just TribusD, and we're a micro SME. We've got lots of experience of how you assemble microelectronics components between myself and my co-director Kevin Cannon. I think in our history we've probably gone through a lot of the developments and made a lot of mistakes in terms of trying to develop solutions and novel ways of doing things. More recently, I say, we've set up a company called TriVSD, and we're looking at whether we can do advanced electronic packaging interconnect with the aims of miniaturization, reducing parasitics, and trying to eliminate interfaces wherever we can, to try and address some of the issues which Martin talked about on the thermal management challenges. So the scope of the presentation, I want to talk a bit initially about high temperature materials and processes, what I did previously, talk about some of the things which are going on in power module assembly, and then just consider, again, as Martin had covered earlier, the push towards things like higher power densities, high operating temperatures, and extended temperature and power cycling ranges, and potentially pointing out some of the areas where there may be issues and where things need to be developed. The picture on the right is a picture of a high temperature hybrid circuit, which I developed with a team with Oxford University and GE a number of years ago in a European project. And our target in that case was to try and develop a system for monitoring the outputs from aero engines, but trying to get to an operating temperature of 250 degrees C. So we're trying to put the electronics into the very hot part of the components and just see how things sort of developed and lasted. And that involved one, developing specific electronic devices, and two, at the time of looking what was available on the market. And thirdly is to say, well, how long would the packaging last to do it? So what we did in the program was we actually developed an ASIC based on a silicon insulator semiconductor technology, which has capabilities for long-term performance, sort of verified performance at 225 degrees C, but could operate up to 250 degrees C. And in some cases, we got it operating up to about 300 degrees C. It was different to most of the normal semiconductor materials in that the actual interconnect metallization on the device was based on tungsten and had an aluminium copper bond pad. And in this particular device, there was no backside metallization. In the hybrid circuit, to do what we had to do, we also then had to put in voltage regulators, clock generators, resistors, capacitors, and transient voltage suppressors, looking at what their capabilities were. And in all cases, when we did the work, we were always at the edge of the technology. And we're always finding that things became derated, things didn't perform at the high temperatures which we expected to see. But one of the major challenges for getting this long-term operation at 250 degrees C was looking at the packaging side. And this is an example of the things which we try to look at in the development, to look at the whole range of different materials to say, well, what could work at 250 degrees C? Generally, we saw epoxy type materials weren't really capable of 150 degrees C. There are some specialized field adhesives which can go beyond 200 degrees C, and I'll explain a little bit more there. We're also sort of towards beyond SAC solders, tin, silver, copper solders. At the time, silver sinter was only just coming onto the market, and copper sinter materials were very much in development. Zinc aluminium, which I'll come on to later, wasn't really around, and we ended up relying on using gold-based materials, inorganic assembly techniques where we could, and a hermetic environment to try and achieve that level operation at 250 degrees C. We also saw at the time is that most of the material suppliers are very comfortable in supplying data on materials and degradation, say for 1,000 hours. They'll give certain numbers of temperature cycles which a material can survive. But what we were looking for, particularly in the aerospace industry, was sort of long-term performance. And we then started cooking things at 250 degrees C for up to about 11,000 hours, which was sort of longer than the life of the oven which we were using to do. And we did start to see some very strange things when we did have organic materials in the package. And the picture on the bottom right shows a growth of whiskers on bond pads from a silver cyanate ester adhesive, which is one of these high temperature materials. But once we cooked it, say, for about 11,000 hours, what we began to saw was really two things. One is material evaporated and deposited and formed these strange whiskers. But we also saw that when we put on barrier layers, things which are supposed to reduce diffusion, then at 11,000 hours, everything's diffused with each other, and you've got a different sort of form of joint to what you might expect from the classic, diffusion layer, barrier layer, which is okay for 1,000 hours or so. So if you're looking for long-term high-temperature performance, then you really need to start looking at how materials interact over that time. So moving on to the traditional power assembly type processes, this is just a picture of what's done normally at the moment, and historically. There are developments which I'll come on to. Most of the traditional ones have used a solder die attach, historically a high melting point solder, which is lead based, which is not going to be accepted in the automotive and most industries now, or possibly again a tin silver copper solder. Aluminium wire bonds are used extensively. There may be gold wires used if you've got a control IC within the package. You have an epoxy molded resin to cover everything, and you can achieve sort of qualification from -55 to +125 with this type of component. You can see here some examples of aluminium wire bonds to a copper and DBC substrate. Multiple wires are used to increase the current capacity, and you'll generally have a smaller wire for a gate connection onto a MOSFET type device. But there's been lots of papers looking at lifetimes of these types of devices, and there are three sort of main failure sort of causes within these power devices when you go through thermal cycling or power cycling. One is the fatigue of the solder in the die attach material. The second can be failure in the wedge bond of the aluminium wire, and thirdly, which I'll come on to next, is that there can be failures in what we call the DBC substrate, which is the copper bonded onto the ceramic substrate. And this is an example here where through thermal cycling, the stresses between the copper and the ceramic can cause failure in the ceramic material. So it's not actually the joint that's failing, it's the stresses are sufficient that the ceramic itself breaks, and what happens is the copper comes off with a sort of a white surface, which is actually the ceramic. And there's lots of developments going on now in terms of looking at different substrate materials to see whether you can improve things, and certainly also designs which try and reduce the stresses when you come to thermal cycling. And some of the talks later today from DK DeLeva may well go into this in a bit more detail of how to overcome these types of failure mechanisms. Other things that are going on in power module assembly and widely reported is use of silver sinter material as the interconnection materials rather than wire bonds. And there are examples here of people who've integrated the power chips onto a DBC substrate, onto a heatsink, and a flexible circuit board with the control components all within the module to do that. And these components are in production in some cases, and it is, you know, a very, very good solution. And again, we've got some talks from Heraeus on some of the latest developments on that later in the day. But again, you've always got to be wary with things like silver within a power package, particularly in the presence of moisture and voltage, is that as you push the temperatures higher and higher, then the silver becomes more mobile, and that could lead to thermomigration or electromigration or a combination of both. This is a recent strip down of a power module commercially available, and you can see here lots of copper in here as opposed to wire bonds for the main power connections, and these can be connected using a solder or a sinter material in there. But what you can see on this picture is that there's also still an aluminium wire bond for gate pads to put in there. So any design which you may have may also have to accommodate, you know, the power connections, but also the lower current connections, which at the moment could still be wire bonds to do that. And on these particular ones here, in this one, then the MOSFETs are mounted onto a DBC substrate on ceramic, again, in that particular application. There's also been lots of work carried out on copper-based interposers between devices, where you can then put copper onto the metallization on the silicon die, and then in this particular case, you then copper wire bond onto the copper layer to get a stronger bond with a copper-based interconnection there. And again, I think we've got a talk later by Richard Dixon of Dicotech Materials talking about copper interconnection systems. And also in the embedded fields, people are also looking at, if they've got control of the MOSFET, is you can then put copper metallization onto the MOSFETs at the foundry, and you can then use plated connections within an embedded PCB using laser drilling and copper field microvias to form the connections there. So there's lots of activities going on in embedded systems, but in this particular case, you've really got to have control of the die which you get from the foundry in order to be able to implement it. This is just an example of where people developed some of the power modules with double-sided cooling, and this has just been announced last year and shows some of the trends in what people are trying to do in terms of getting miniaturized, improved thermal performance, and moving towards more traditional, moving away from more traditional single-sided cooling type solutions to double-sided cooling, to try and overcome some of the difficulties of getting heat out from devices. So Martin talked about, say, increasing adoption of wide bandgap semiconductors. Where the trends are going towards is, say, trying to make the shortest possible interconnections so that you can reduce parasitics, double-sided cooling if you can, and then integration of gate drivers so that you get more control nearer to the MOSFETs to doing it. And what people are trying to do in these particular cases is reduce or eliminate wire bonds where they can, looking towards developing sinter-compatible device metallizations. And perhaps the one which is a bit more difficult for people already using power modules is that everything's set up for single-sided cooling in terms of form and fit within larger scale modules. If you suddenly try to introduce double-sided cooling, this could cause sort of down the line headaches for the module integrators, because suddenly, rather than having a single-sided access, you may have double-sided cooling with different plates forming onto the module, which could then cause a whole difference in how people try to engineer the next level up for the module. So there's always got to be that compromise between, you know, what theoretically you can do from the packaging side and what then could be done for integrating within that in the larger sort of system level approach. So if we look back at the chart, which I call die attach for power modules, and see what's available, what we can see is that the thermal conductivity requirements sort of preclude most conductive adhesives for die attach for getting power out of devices. If you're looking towards something towards 175 degrees C operation, SAC solders are theoretically okay to be used, but as you push the temperature or push the thermal cycling type areas there, you really need to pay attention to things like intermetallic growth and alloy selection. For silver and copper sinter materials, I think there's very attractive areas there, but certainly on the silver side, you've got to be very, very careful about migration, and certainly on the copper side, you've really got to be careful about the oxidation issues on copper and how you protect the copper from oxidation. Going towards 250 degrees C operation, then you're getting into more exotic sort of die attach or substrate attached materials such as zinc aluminium and transient liquid phase soldering, which I'll come on to a little bit more difficult come on to. But both of those materials, processing becomes much more difficult than applying a normal solder. So these slides, I'll just give a very, very quick run through of some of the aspects of silver sintering. And as I say, I think there will be further talks later in the day, which will go into a bit more detail. And I'll focus on the sort of negative side rather than the positive side in these slides of going through, you know, what you need to think about for implementing these types of things. And with a silver sinter material, pressure to achieve low voids is a debate which continues, and there's a whole range of materials which are around, which could be in film form or paste form to use. Sometimes the sintering time is relatively long. Roughness of the surface may have effects on the joint reproducibility. And I think the last 2 points, as we're pushing towards higher temperatures and areas like that, is long-term diffusion interactions, electromigration, areas like that could leave weak zones within the modules. Copper sintering is relatively recent process being developed, and I think Richard will talk about that later in the day. And the attractions are quite obvious in terms of pricing and in terms of potential to reduce some of the stresses. But again, focusing on the negative, again, which I'm sure we shouldn't do, is all about processing copper, processing inert gas, trying to reduce oxidation, looking at how you control thicknesses. And in this particular case, I put commercial materials not currently widely available. I think that situation is changing, and there will be more copper paste coming on the market in the future. The zinc aluminium or aluminium zinc solder die process is a bit of an odd one. There's been a lot of development, particularly in Japan, looking at this as a lower cost alternative to other solders. It's got potential for high temperature operation because the eutectic point is above 380 degrees C. But zinc and aluminium are very sort of active materials. So wettability, affinity for oxygen, need for vacuum processing, how you apply metallization to the die backside and substrate, and controlling that are some of the key areas there. So if you can invest a lot in equipment and handling and complete control of the supply chain, then there's a chance with aluminium zinc soldering, but it's not going to be an immediate replacement for SAC soldering, which you can put through an oven, and it will work pretty much every time. And so finally, just in this quick review, the transient liquid phase route of using a low melting point material in between high melting point material, and then relying on melting into diffusion, has had a lot of action research-wise, and has the potential to get towards higher temperature operation using lower temperature materials, and also using common materials such as copper and tin to achieve it. But realistically, it relies on growth of intermetallic materials. There's complicated processing because you've really got to have clean surfaces to get the effect, and it's difficult to avoid void-free interfaces. Sorry, it's difficult to achieve void-free interfaces when you're going through. And this is just an example of from the phase diagram of where you go through doing that through different heating and temperature endurances, and you can, let's say, achieve from tin at 232 degrees C melting point, you can achieve compounds which are relatively stable at 676 degrees C, but in all these things, the intermetallics still grow. They still may be brittle, and there still may be voids in terms of doing that. So, what some of the areas which people are looking at in terms of trying to get towards achieving higher temperature performance falls into sort of two categories. There's most MOSFET devices on the market are normally metallized with aluminium because they're set up for wire bonding. So you generally then have to do something to it to try and make it stable for something like sintering or soldering. If you've got access to foundry, then there are copper metallizations available which can get you into a different scenario, but they're not so available on the open market to do it. So plating of the aluminium using electroless nickel, and electroless nickel, electroless palladium, and immersion gold are ways of converting the aluminium top surface to something which could be suitable for sintering and soldering. But going to high temperatures, you also need to be aware that within the electroless nickel plating, there's a level of phosphorus, and above 250 degrees C, nickel phosphides begin to form, which by their nature as intermetallics, they are brittle. So just going through and saying, we're using NIG or NEPIG plating for these types of things mean you could still have problems as you go towards high temperatures. We had previously some of the things with using sintering material on copper foils, and again, you've then got with an aluminium metallization different materials, and there may be temperature limitations, but also could be corrosion in the presence of halide and sulfides, which quite often find themselves into epoxy molding compounds and things like that. I've mentioned things previously about oxidation copper. With copper control all the way through, then there are possibilities of creating a whole copper interconnect system, which I think ultimately is where things are going in the future. I'm realizing I'm running out of time, so just to talk about very, very quickly some of the dominant failure mechanisms, electronic packaging. I've talked about a lot of these areas there, which can be looked at when you get the slides on review. Voids and delaminations, we've talked about cleaning, metallizations on diffusion reactions, are all parts of things of looking at if voids and delaminations occur. Cracks in the die are very much courtesy of whether you have thermal expansion mismatches between die and substrates and the materials which you use between them. And cracks in a joint are very much, again, the fatigue resistance of the material which you use for the interconnect are very, very critical in terms of the interconnect materials. So this final slide talks again about electro and thermal migration, and again, be very, very careful about what happens at higher temperature or in thermal cycling is the materials can move and they're not stable. So my final remarks, really going towards high temperature systems, you should always try to design wherever possible for monometallic interconnection systems, so that you can try and reduce the effects of intermetallic and void formation. We've done, say, historically, a lot of work on gold-based, non-organic and hermetic systems, but realistically, they're very, very niche. And looking for mass production of power modules, the cost involved in doing that mean that they're not particularly viable. Copper-based systems, I think, are showing promise, but you really need access to semiconductor foundry to deposit the copper on metallizations, and you really need to look at effects of oxidation. And the final warning one is about use of dissimilar materials, is pushing towards high temperatures. Always think about diffusion and migration interactions, because they can cause reduction in product lifetime, premature failures, and those things will be accelerated as power densities and operating temperatures increase. So thank you very much for your attention. I think I'm just about on time, Liam. Happy to take any questions now or at the end of the session.
Yeah, many thanks, Steve. It doesn't look like we've got any questions in at this stage, but if people do have questions at any point through the day, just feel free to drop them in the question box and we can answer them as we go through, rather than having to wait at the end of each speaker. So yeah, thanks very much, Steve. That was really great in-depth information. And obviously, if we do go towards higher temperature electronics, these are the areas of research that are going to be fundamental to enable this to happen. So thanks very much for that. We're going to have to move on to our next speaker and the final one for this first session. So it gives me pleasure to introduce Mark Johnson from Nottingham University. Mark's been working in power electronics for a number of years and is well known in the area. And he's also the director of the EPSRC Centre for Power Electronics. And Mark's talk is going to be on packaging and integration solutions for wide bandgap powered electronics. So over to you, Mark.
Okay. Good stuff. Okay. Good morning, everybody. Hopefully you can see the slides there. And welcome to a talk which I think we've had a very good couple of previous talks introducing firstly wide bandgap semiconductors and secondly some of the challenges associated with packaging. So I'm going to take a slightly higher level to this and talk more about from packaging into converters and into power electronic systems. Acknowledgements to a large number of people, including colleagues in RAM Innovations and the Thinking Pod Innovations. So none of this work is really mine alone. I'll start by giving a quick introduction to where I see the differences between the challenges for, say, silicon power electronics and wide bandgap. That moves on into discussion of power electronic building blocks as a potential solution, and then a couple of case studies, one based on silicon carbide for an integrated drive and the other on a gallium nitride embedded die solution. So challenges for power electronics, and there's nothing really new on this slide. Reduce costs, everything from materials going in to end-of-life recycling, increased efficiency, which depending on what application you're looking at can just mean point efficiency or reduced losses through the whole life of the product. Increased power density, a lot of interest in applying wide bandgap for that particular challenge. Ease of use, and this is really where some of the challenges for wide bandgap particularly come to the fore, because ease of use and ease of application of wide bandgap is often one of the end users' biggest nightmares. Environmental tolerance, of course, we've heard a lot from Steve about higher temperature operation, but vibration, shock, and other environmental extremes are all very important in that sector. Finally, and Martin touched on it earlier, skills. There is a massive shortage of well-qualified people in this area, so the training and reskilling of people for power electronics is one of our major concerns. So if you look at those things together, reduced costs, increased efficiency, making the things smaller, lighter, cheaper, all of those things interact, and of course, as usual, you don't get everything at the same time, so it's always a compromise. Emphasizing one thing tends to degrade performance in other areas. So the whole point about this talk, and I think the previous two, is that wide bandgap devices, in particular silicon carbide, gallium nitride at the moment, offer opportunities for increased efficiency, largely deriving from the use of majority carrier rather than bipolar devices at high voltages, or for power electronics at least. That in principle allows you to reduce the amount of device area, increasing in theory potential power density, and allowing you to use less semiconductor material, which for these devices and their inherently more expensive material technologies is important. The one I want to focus on really is increased switching speeds, which we'll come on to in much more detail. The principle there is that higher switching frequencies allow you to use smaller passive components, depending on the type of power electronic converter you're looking at. That may or may not be particularly important, but it's certainly one of the key factors that allows you to get a higher power density. And by getting rid of some of those passives, you can reduce your bill of material. So in principle, trading off more expensive semiconductor for cheaper or fewer passives is a real opportunity. Higher temperature operation is clearly a potential for wide bandgap, although one that's currently significantly restricted by the packaging technology. The trade-off, of course, is that higher temperature should allow you to create a more dense thermal management system, but that in itself requires you to have higher temperature capability throughout, something that doesn't always follow from the point of view of passive components. So what makes wide bandgap different to silicon? Well, you could say that all of the previous benefits to using power electronics and the challenges associated with power electronics apply equally to silicon and wide bandgap. The real thing that makes a difference is not so much how you get the heat out, because you've got to do that all the time. It's really on the electromagnetic side, and the fact that these devices switch more quickly is both an opportunity and a challenge. So it's worth looking at things from an electromagnetic point of view. Anything to do with electromagnetics tends to send people into fits of worries about Maxwell's equations. Well, don't worry, we're not going to focus on that today. Instead, we're going to look a little bit more generally at some of the interactions. So, first things to remember: if you've got a changing current or a changing electromagnetic field, you will generate EMI. You will generate unintentional coupling between different elements in a circuit, and those things together provide you with challenges, not just for wide bandgap, but silicon devices as well. The particular challenge with wide bandgap is that because you've got faster switching, greater rates of change of voltage and current, the issues associated with EMI become much more challenging. So this is moving into the circuit side from the device side in itself. And what we're looking at is just a very simple copper circuit with a few red components which are there to emphasize the effect of passive parasitics. So we have influence from things like parasitic inductance, so simply connecting things up. You have a current flowing in a conductor producing a magnetic field. That is an inductor, not necessarily just a wire linking 2 points on a circuit diagram. Because you've got interactions between magnetic fields, you end up with coupling. So one of the most challenging issues for power electronics is unintentional coupling in things like the gate circuits of power devices, leading to false triggering interactions, etc. Furthermore, high rates of change of voltage on an isolated drive can cause parasitically coupled currents to flow through the admittedly small but still significant capacitances that exist in the layout or in the gate drive component. So that's another source of things getting into parts of the circuit you'd rather not. Finally, you've got parasitic capacitances between switching nodes, the thing that you're intentionally wanting to change voltage quickly, and the elements of the circuit, for example, the heatsink, grounded parts of the system that you do not want to couple particularly to high-speed changing voltages. So all of this results in a very unpleasant mix of passives and active components, resulting in a wide range of possible parasitic and resonant effects, false oscillations and gating due to coupling, and common mode induced issues due to very high dV by dt. So you're up against it really, bearing in mind that your average wide bandgap device can switch probably at least 10 times more quickly than the equivalent silicon structure for the same voltage. So what do we do about this? So these rapidly changing voltages and current and unintentional couplings between various elements of the circuit, of course, produce electromagnetic interference. And that can circulate within the converter, and illustrated within that little green box is a converter of some description, and can also circulate outside. So you have the external paths. The dark green lines on the diagram are to indicate differential mode electromagnetic interference coupling, whereas the purple line is a common mode loop. Either way, higher rates of change of voltage and current only make things worse. And the big challenge with wide bandgap then is to control EMI. Once you've let it out, in other words, if you let it outside of the converter box, you've got a very difficult task externally getting it to go back in. So better not to let it out in the first place is what I say. The fallback from that really is that rather than thinking about EMI confinement after the event, which tends to be historically the approach of solving EMI problems in power electronics, you really do need to focus on building EMI confinement into the circuit, into the packaging at the appropriate level, and the appropriate level is before it has chance to escape. To contain EMI is not that difficult. You just put it in a Faraday cage. Unfortunately, if you complete a Faraday cage, you can't get any electrical signals in and out. So you've got to provide careful amounts of screening and shielding. But at the same time, if you do have connections going through your case, in other words, you can't avoid having control, power in, power out, you've got to make sure that those things are properly filtered. If you get that right, on the other hand, and confine all of the EMI inside the box or inside the screen, you can in fact eliminate the possibility of EMI circulating in the external circuit. And that's really what we want to allude to in terms of wide bandgap, because the issues with EMI just become more difficult if you want to fully utilize the very high switching speed of the devices. That leads on to the proposal that you can't just throw a converter together using conventional approaches to packaging. You've got to really look at the parasitics. You've got to look at how you can achieve a compact physical layout, optimize the EMI performance, and at the same time ensure you can still get the heat out. So again, it's one of these awkward trade-offs where the things you might like to do to confine electromagnetic fields may not be compatible with producing an optimal thermal path. And this is where the end user comes in, because many people who would like to utilize wide bandgap find that it's not easy to do because they're unable to re-engineer or unwilling to re-engineer their systems to start with a complete blank sheet of paper. Like for like substitution, particularly with devices made in silicon carbide, has been a real it's been a good thing in the sense that people think, yeah, I can get an extra factor of 2 on switching frequency. I'll drop my silicon carbide MOSFET in place of my silicon IGBT. But unfortunately, you're not really utilizing the device properly. And if you try and utilize it properly, you end up with all these EMI problems I've just alluded to. So that's a danger for the technology because it may lead to some degree of stagnation. It also prevents other people entering the sector and taking up newer technologies like gallium nitride, which are inherently faster and inherently, therefore, more difficult to deal with from this point of view. So, where are things going? This is an extract from the IEEE ITRW, the International Technology Roadmap for Wide Bandgap Semiconductors, which shows one possible set of progressions in terms of how packaging for power electronics and for power modules in particular is going to evolve. And essentially, you've got two things going on here. One is that for applications where switching frequency is less important, and the things highlighted there are silicon carbide inverters and high voltage, you've got options to use conventional packaging, which has been adapted, modified, improved to create better thermal performance or improved to create lower inductance. And there are plenty of examples of those around. If you start to look at the very high switching frequency applications, for example, DC to DC, you've got to really worry about how you build your circuit, not just how you package a device. And the simple fact is you can't use physically large objects. Use physically large objects, you end up with physically large circulating current paths and therefore big inductances, smaller cells, smaller surface mount components with embedding or stacked substrates. Working towards a 3D layout, in fact, is where things are probably heading for the very high frequency applications. However, that's uncharted territory for many module manufacturers and also for the majority of end users. So there is an opportunity there to look at new approaches to things like power electronic building blocks. Historically, at sort of kilowatt levels and above, you've had separate modules or separate power devices, separate filter components, separate gate drives, etc. Things have been very much designed separately, developed separately by separate manufacturers, and then assembled, often by hand in a fairly intensive process, bolting things together at the end of the day. So if you start to look at trying to do that with higher switching speeds, it just doesn't work, and you've got to make the actual commutation cells themselves much smaller. It's driving you towards using more surface mount, embedded and stacked technologies to create compact 3D layouts, and it's something that the ITRW highlights for faster switching. It's also desirable to integrate as much of the control, thermal management and EMI suppression that you can at that stage to ensure that you've got a controlled design. That gives you the opportunity to give the end user something that they can literally take off the shelf and they know will work in their application, rather than worrying about EMI and other issues such as thermal management after the event. So we all have probably come across low power, few hundreds of watts, probably down to several hundreds of milliwatts, little DC to DC converters, which are fabricated by many different manufacturers as a single package integrated assembly, work very well and cover all sorts of applications. However, that approach has not really been tried at the sort of kilowatt to low megawatt level. Can that be done in a cost-effective way that meets the needs? And the question then is, how do things evolve? So if you look at packaging for low power semiconductors, they tend to be surface mount, they tend to be small. Looking towards higher levels of integration, you've got a number of examples of people using PCB embedding type approaches or complex assemblies such as those illustrated there from Vicor, and those are capable of producing very high power density assemblies from what are by and large either silicon or silicon carbide or gallium nitride devices. And this really falls into a category of what I refer to as additive embedded converters in package. So they're sort of built up from the ground and assembled as one block. There's then a second school of thought which has evolved really from the high power end of power modules, where you take discrete power modules and you sort of assemble those using a fairly conventional approach. The Semicron skip and sky modules are examples of this, where you have power devices assembled onto DBC substrates in a fairly conventional way and then packaged with a variety of different conventional circuit board technology in a single package to produce a converter. So the question is, how do you fuse those together? So on the left you've got the low power, on the right you've got the high power route. One possible way forward, therefore, is to look at what sort of things we need inside a building block, and you cannot just build a 1 megawatt building block. That's difficult. It is always a parallel combination, whether it's paralleled in a power module or paralleled at circuit level. So it has to be scalable. You've got to be able to connect smaller modules in parallel or in series. Each of those modules has got to have its own embedded control. It's got to have its own gate signals. It's got to be able to carry out the functions of control at the local level. It's also got to have EMI containment and a thermal interface to allow you to get the heat out. Okay, so the advantage of that is, in principle, that you can contain the EMI, you can get a small, compact, low-weight solution. You can, if you wish, then build up bigger converters by connecting them in parallel or series, depending on the topology. And perhaps this gives you a route to simplified certification and qualification, because you only need to do it for the one building block. Okay, so power electronic building blocks have been around in various different forms, as we've seen, and I just want to illustrate a couple of things that the university has been involved in over the past 4 or 5 years, which illustrate how we can move towards either an approach for silicon carbide based on assemblies of substrates, or towards gallium nitride solutions based on a die embedding approach. And this just illustrates some work we did in collaboration with a number of other universities to look at technologies for creating an integrated drive where the power electronics is embedded within the machine housing. I won't go into the details of the machine, although it's very interesting in itself, really the topic of the discussion here. Needless to say, what we've got is a 9-phase system, and you'll see how that translates into an assembled bit of power electronics. So if you think about the machine at the bottom of the image there, you've got some power modules, which we'll look at in a bit more detail in a minute. On top of that, you've got layered technology. The gate drives and the decoupling capacitors for the power commutation side of things have to be close to the device, but you can't put them in the same place, so one has to go above the other. And this structured approach allows you to create what is essentially a 3D commutation loop to minimize the inductance whilst keeping the gate drive as close as you can to the device. And both of those things are essential if you're going to operate at high switching frequency. But the rest of that is really to do with the drive control. Again, I'm not going to go into that in any detail, but it does illustrate some of the complexity there. When you start to look at this, you realize that the microelectronic side of it is probably takes up as much space in this case as the power electronics. So moving down into the various layers, we've got a gate drive board. Probably realized by now that with a 9-phase or 9-half bridge system as this is, you've got 9 segments arranged around the periphery of the machine. So 9 separate gate drives, each one driving a half bridge, and 9 circuit boards effectively providing all of that. In fact, they're arranged onto one circuit board, but as you can see, it's quite clearly partitioned. Beneath that, you've got decoupling capacitors, and then you've got the power substrate assembly, which is based on a DVC technology with silicon carbide MOSFETs, in this case 6 of them arranged in 2 lots of 3 in parallel. And on the actual power substrate itself, there are those devices, and then a current sensing resistor and a temperature sensor for each of the 9 half bridges. The interconnect for that is made with a flexible PCB to minimize the inductance in the commutation loop, and also to provide a vertical interconnection path to the boards above. So above that, you've got the decoupling capacitance, and then above that, you've got the gate drive. So the whole thing is then mounted down on top of directly on top of the windings. So the stator windings poking up there through PCBs are interfaced directly onto the substrate. So the wires in this case actually come through the substrates and are bonded, soldered in this case, onto the substrate. That PCB you can see in the image in the left is the PCB indicated at the left-hand side of the cross section, and then the substrate is connected through a pillar which goes through the substrate and is bonded through. So you've got a slightly more complicated substrate assembly that's got through holes in it. Okay, so that gives some idea of what's going on. And one of the big challenges with any integrated drive, particularly one that's at any sort of significant power level, is how you cool it. And here the challenge was to cool the power electronics and ensure that the temperature of the power electronics was maintained at a low level. So the challenge really is firstly how to get the cooling liquid in there, so it's a water glycol cooling circuit, and secondly how to ensure that coolant can be used effectively to cool the substrate. And the technique used here is not a new one, but just using jet impingement onto the back of the substrate to provide an enhanced heat transfer coefficient, and then recovering that fluid, which then is fed through the stator windings of the machine. So the power electronics are cooled first, and then the coolant is diverted into the windings. Okay, so that was the first of 2 case studies. The second one is more of an embedded dye solution, and this is some work that was conducted with RAM Innovations, an SME based in North Wales, and with the Thinking Pod Innovations, who are a spin out from the University of Nottingham. So chip embedding is widely used in microelectronic applications, less so in power, where you're looking at higher current interconnects, one of the big challenges, and also thermal management becomes an issue. So PCB materials not known for their good thermal conductivity. So the issues really to address here were how to create interconnects that were in a PCB technology but capable of dealing with potentially hundreds of amps, at the same time ensuring that you can get the heat out of the dies. And finally, making sure that whatever process you come up with is still compatible with a standard, as near as possible, standard PCB assembly process. So the embedding thing, and I think Steve mentioned this briefly, is really about PCB technology and creating a mechanism for embedding die, and there's no difference between the microelectronic approach and the power approach, at least in principle. So you're creating a pocket in a PCB, putting a die in the hole, filling it up, and then overplating to create the interconnect. That's really simplifying the process and burying a whole load of issues. For example, plating to non-copper metallizations is not an option, so how do you get all your dies copper metallized? Okay, so we'll gloss over that one. Thankfully for gallium nitride, they come, well, depending on whose devices, I'm not going to publicize them, but GaN systems, the dies are copper metallized, which lends itself to this particular approach. The equal possibility exists for silicon carbide, but actually getting dies in a format that allows you to process them in this way is a little bit more challenging, because you can't just go to a manufacturer at the moment without very deep pockets and say, can I have a copper metallized silicon carbide die? So the benefits to this are that with an interconnect that is inherently planar and three-dimensional, you can create a very low inductance layout. And what you can see rotating away merrily on the right, I hope, is an image of an X-ray tomography image of two embedded gallium nitride HFETs in a half-bridge configuration. And you can see the finger connections, the gate finger connections to the top of the dies, which then are fed upwards through laser drilled holes, which are then plated, and those plated holes are then partly connected to tracks which form part of a PCB layered structure. So you can see the thing there. It's probably got you can see two layers of copper above the die. One is the interconnect layer, and the second layer is essentially where the pads are brought out onto the surface. So if you look at the article itself, the photograph of it down in the bottom left, you can see those top layer pads which are there for the gate and the power connections for the half bridge. So as a simple example, it illustrates what you can do with this technology. It also illustrates here that you can get reasonably good interconnect that's functioning well even at high current and after significant thermal exposure. So the important thing, and one of the important things we wanted to look at that with this technology, was whether it could match or even surpass what we could achieve with a conventional wire bonded package, and this is really an acid test for any new interconnect technology. The good news is that with this this simple demonstrator, you can see the images there on the bottom of that slide show the interconnect at various thermal cycle stages. The one on the left is actually the initial state. The one in the middle is after 500 cycles of minus 50 to, I can't even see what that says on there now, 100 and whatever it was degrees. So a fairly extreme thermal cycling range. 500 cycles in the middle and 1,000 cycles on the outside. I should really hide that, shouldn't I? 150.
Hi, Mark. We're slightly overrunning here, but if we could wrap up in a couple of minutes, that'd be great.
Yeah. I didn't hear your bell.
That'll be my mistake. Sorry.
All right. So we are at the end. Future perspectives. So I think you've seen there possibly two ways of progressing from conventional type assembly mechanisms to more compact, more integrated approaches to creating commutation cells with some degree of either embedding or substrate mounted components, together with surface mounted passives and thermal management integrated into that process. So the way in which that goes forward it's going to really be determined by how the materials and manufacturing technologies evolve. So on the one hand, you've got the conventional approaches which are enhanced by things like sintering, things like planar interconnect technologies, but they've got to be low cost, they've got to be scalable, and they've got to be volume capable. And the same applies to the PCB embedding approach. It's no good if you can't realize that in a low cost scalable way. So at the end of it, if you can realize these things using industry standard processes, or you can establish industry standard processes for additive and subtractive layer techniques for component embedding, then you can move forward with the embedding route. It's attractive, but at the moment there are very few suppliers on the market. In fact, no one offering a fully integrated approach to this, and therefore it's a right topic for further research and development. And the conclusions are really the obvious ones, in the sense that getting the best performance out of wide bandgap and high-speed switching is going to require integrated assemblies with integrated thermal and electromagnetic management, sensing and control functions. So we're moving, I think, into an era where converter in package products and building blocks are likely to become more prevalent for the majority of end users, and that's going to require the equivalent manufacturing processes to catch up. And I guess the challenge for people who are involved in that industry is whether that comes from the power module manufacturer end, or whether it comes from the PCB and component or converter assembly end. One has to move up market to do that, and the other one has to move down market to do that. So it's an interesting question to debate. I'll finish on that note. So thank you very much for your attention, and if you have any questions, I have no idea how you're going to address that. So, thank you, Liam.
Many thanks, Mark. That was really great, and it obviously shows the challenges with the packaging technology for these wide bandgap devices, and some of the integration techniques aren't quite as simple, like you say, as just dropping it in. So thanks very much. That was really in depth. We don't have any questions specifically come in for your talk, but like I say, if anyone does have questions that pop in their heads as a day, pop them in and we can get them answered by the speakers as we go along. So the first, from the first speaker, we had a question for Martin that he's been able to answer during the presentations. So it was, could you expand on the skills funding to come, and will this be focused on undergraduates, postgraduates and apprentices, etc., within companies or within universities? And the response to that question is it's very much a work in progress at the moment, and it's probably likely to be more aimed at retraining, but it won't be funding any undergraduate or postgraduate studies. So hopefully that answers the question, but feel free to get in touch with Martin directly, and if you have more questions on that. So to that point, we come to the end of our first session. I hope that's been really informative for everyone. I've really enjoyed it, and hopefully you have too. So for now, what we're going to do is just run a quick survey in the break here. So if what I'll do is pop the link into the chat area. It literally takes less than a minute just to get some ideas on what your thoughts are around temperature on this first survey as well. So thanks very much everyone for this first session. We'll reconvene again at 11:30. So thank you very much.